All right, so let me carefully phrase the counting theorem. Okay, so the counting theorem is this really useful thing in linear algebra that maybe doesn't replace, but really strongly supplements some of the tools I've been using. So the counting theorem says pretty simply that the dimension of the null space of a matrix is the dimension of the domain of A minus the dimension of the column space of A. And another way of saying the dimension of the column space of A is to say the rank of A. So these two quantities are equal. I'm gonna flip back and forth pretty strongly between which one I put in there. Just know that those two quantities are equal. We talked a little bit about why they were equal in a different video, but just for folks who haven't heard that or who are joining us in this new video, the column space of A is the range of A, which is just all the linear combinations of the columns. The rank is the number of linearly independent columns. And so the dimension of this span of columns is in fact just the number of linearly independent things in there. This will occasionally get rephrased as the rank of A is the dimension of the domain of A minus the dimension of the null space of A. It should be noted that all these things are small whole numbers, so you can feel free to rearrange this algebraically if you want. I suppose the third rearrangement that's kind of useful is the dimension of the domain of A is the sum of the rank and the dimension of the null space. You guys good with algebraic rearrangements at least?
I feel like most of the time the dimension of the domain is going to be kind of apparent, or there are going to be instances where we need to find it.
Not for a very long while, at least. So there'll come a time where we kind of forget the idea of matrices for just a hot minute and then come back to it. But for the most part, yeah. So if we have an n by m matrix, wait, do I usually do that the other way? I usually do that the other way. It's m by n. So a matrix that's m by n maps Rn into Rm, right? So in this case, this n is this dimension of the domain object. And so if we were to rephrase yet again, it's the dimension of the domain n is the rank plus, this is kind of often abbreviated as nullity, which is just the dimension of the null space. Everybody good with that? All right. So essentially the idea behind proving this, and I'm gonna kind of just sketch a little proof because I think I've taken enough time with this. It's not super counterintuitive. I'm gonna look at this one. That's kind of the one I'm thinking of here. And I'm going to think to myself, all right, so a vector in the domain, right? So this kind of n is the number of directions, and I'm maybe saying directions in quotes here, in the domain. So when I think about this whole space, right? So I've got this big wobbly space. It's really just a big flat thing, right? and I'm going to hit a matrix against this. Now, when I hit this matrix against this thing, I have to remember that the matrix is linear, right? So I'm remembering that the kind of fundamental thing I'm recalling is that A done to a constant, right, a scalar times x, is that scalar times A of x. You guys with me on that? So this is scalar multiples float through linear operators or matrices. And there's also this case where if I have A of x plus y, that's ax plus ay, right? You guys with me on those two things? So these two things together are going to tell me that a direction either all goes to 0 or all doesn't go to 0. You guys with me on this? Because these guys look like the subspace things, right? You guys see that? So what I'm going to do is I'm going to think, all right, so the number of directions in my domain A are R. This is the number, oops, I guess I'm using inconsistent notation here. R, which would be the number of directions not going to 0. Plus the nullity. And the nullity is the number of directions that go where?
Zero.
Perfect. In other words, this thing really amounts, like the counting theorem, all it amounts to is, look, bro, vectors, they either go to 0 or they don't. It takes a whole direction to 0, or it takes a whole direction to not 0. So if I think about all the directions that I have available in the domain, well, one at a time, they either go to 0 or they don't, right? And so the number of directions total is the number of ones that go to 0 and the number of ones that don't. Is that kind of jive?
Yeah.
Okay, there's one more thing here, which is a little bit obvious, but also maybe worth recognizing, which is that the rank can't be bigger than the space you're mapping into. Does that make sense? So the rank of a matrix A has to be smaller than what? Or equal to? What's the size of the space I'm aiming at here?
The dimension of the domain, it has to be smaller than or equal to.
Close.
Oh.
Where is it going? It's going into m-dimensional space, right? Remember the rank of A is the dimension of the column space. The column space fits in the image, right? It's in the codomain. So this can't exceed the size of the codomain. Does that make sense? Like if you're going to take 10-dimensional space and you're going to jam it into 2-dimensional space, the rank can't be bigger than 2 because it's got to fit into the space you're aiming at. Does that follow? Also, everything in the counting theorem here, all of these, the dimensions and the ranks, they all have to be 0 or bigger, right? So they have to be positive whole numbers. Well, sorry, they have to be whole numbers. They don't have to be positive. They can't all be 0. That is an important thing. Well, okay, some of them can't be 0. the dimension of the domain probably is not 0, right? I guess it technically can be if you have the matrix that goes from the 0 vector to the 0 vector is a 0 by 0 matrix. Just doesn't have anything. Fuck it. All right, ignore that edge case. Any questions on this whole thing? The thing I really want you to take is this. The dimension of the domain is the rank plus the nullity. That's what I want you to have. And then it's also good to know that the rank can't exceed the dimension of the space you're mapping into. That should get you most of these dimensionality questions. Cool.